Okay. Now you remember last session we've been talking about inverter, which circuit for converter used to convert DC into AC. We discussed the one leg converter. Just to remind you, okay, just to remind you, here is, oh, sorry, okay, is my leg A. Okay, here is the supply VD. I use here two identical capacitance to split the voltage between them, so I can have 1/2. I mean, we make it in this way just for one reason, to distinguish between one leg and two legs. Otherwise, here we don't need them. Here in this circuit, we don't need these two let me say, capacitances. Directly, we have leg A, leg B. Okay, and as you can see here, TA positive and TA negative. For leg A, one to conduct the positive part or current, and the second the negative current or voltage. Sorry. So also we connect anti-parallel diodes, freewheeling diodes. As you remember, we put them to make another path for the current to follow through when its reverse is direction. We duplicate this leg and add another leg, we call it leg B. It's have the same thing, also switch connected anti-parallel with diodes, okay? And the load is connected to the middle of leg A and the middle of leg B. So load will be connected here, okay, as you can see. And the output voltage is the difference between voltage across leg A and voltage across leg B. Now, how the current will follow? Have a look. The current will come first if we switch on A positive, let me say, TA positive and TB negative to conduct the positive current and voltage, sorry, in this way, back through this switch to the supply. Let me change the color, okay? Okay, now if I switch TB positive and TA negative, the current now will follow through this switch and back to the supply. What I want you to do here actually, okay, is let me change the color, okay, 1 second. To focus on these two arrows, one of them in direction and the other in the different opposite direction, which means my voltage built on the load will be positive, negative, and so on. Sorry, this way, yeah. Positive, as you can see here, positive, negative. You see? Now, this will give double the voltage produced by one leg. So if it is two legs, it means 2 by VD/2, it means VD. The output will be VD. Now, if we keep this in our mind, then we can say everything discussed for one leg applied here. The only difference here is we have VD, not VD/2. So if we repeat the discussion for, let me say, linear modulation, over modulation, it's the same. Only one difference is VD, not VD/2. So the fundamental output voltage will be MA VD times VD, not VD/2 for linear modulation. And you can see here, when I compare control with triangle, we discussed this last session for half bridge, I mean one leg. What we got the same signal here. What is the difference here from VD to minus VD? While in the previous leg, it was from VD/2 to minus VD/2. One more issue also to remind you here is that the voltage between here and here, the fluctuation between the minimum voltage and the maximum voltage. This is because this is bipolar. Later on, when I discuss unipolar, it means control leg A separately from controlling leg B. We will see that the voltage will take different shape. Also, for over modulation, when MA greater than 1, okay, we know that V maximum will be, or let me say fundamental maximum will be greater than Vd and lower than 4 over pi Vd. We mentioned why 4 over pi, because square wave, when we go for the square wave, if you, just to remind you, you remember, this is, let me say, the curve. It is in this way, as you can see here. Here up to here, MA here equal 1, and here greater than 1. So this is the linear. Now here it takes the parabola curve, and then it will continue for square wave. This is discussed in the previous session. Now let's apply the same example discussed in the previous session on full bridge, 2 legs. So it is the same example. He told me that now it is full bridge. It is full bridge. It is not anymore half a bridge, full bridge. The same voltage, the same amplitude modulation, the same frequency modulation, 39, and the same fundamental frequency. Also, he asked me to find the RMS value of the output voltage plus some dominant frequency, similar to the previous example. Now, when I come here, I will find that because it is RMS, requested to find RMS, I will divide by square root 2. Because it is full bridge, I will multiply Vd over 2 by 2. So it means Vd the output. And this is the ratio need to be calculated. Now, I have Vd, I multiply it, I divide it by square root 2, it gives me this value. Now, what I need from the table, I have to get this ratio. From the table, I need to get this ratio. So you see, I will find fundamental 2mf plus minus mf plus minus 1 plus minus 2. These are the two, okay, and 2mf plus minus 2. Now, how we find them? We go to the table. Let me take you to the table. Now, this is the fundamental, right? Now, how much my MA, my amplitude modulation is 0.8. So I'm talking about this column for only, okay? If it is fundamental, I will multiply by 0.8. If it is equal to MF is 39, then I multiply by 0.818. Let me check. For fundamental, you see I multiply by 0.8. For MF for 39, I multiply by 0.818, and so on. We repeat the same example discussed in last session, but the only difference it seems to be is here the voltage is Vd, not Vd over 2. Now, one more issue interested to be mentioned here. I always say that, yes, we need to convert in power electronics from AC to DC, DC to AC, DC to DC, AC to AC, but harmonics is an issue, is a problem affecting both the load and the supply. We need to consider it, otherwise we will have many, let me say, problem accumulated later on. We will discuss this in the application when we reach the disturbances. But now, this is my inverter, okay? This is my inverter. Half a bridge, full bridge, doesn't matter. Now, what is important is this is my load, which is DC, let me say AC motor, and this is my supply. Let me say it is battery, it is solar cell, it is a rectifier, whatever it is, DC-DC converter. Now, harmonics will affect my load and my supply. What should I do? Usually, we use filters to reduce the harmonics. You studied this before. Filter use to observe or attenuate or mitigate or reduce or cancel the harmonics. So I will put filter on the output of the inverter and filter on the input of the inverter. Now, if I assume that the circuit here is lossless, it means input equal output. It means, as example here, output, I output, V output equal input, VD, ID star. Okay, VD, ID star. By the way, I just to distinguish between ID star before the filter here and after the filter. Okay. Now, if I go through this, I know that from the discussion that output voltage is the sinusoidal waveform, square root 2 VO sine omega t. And if I calculate I, it will be also maximum current here, Sine omega t minus phi is the phase shift between current and voltage. Very easy. Now, if I substitute it here and here, V and I, both, and divide by Vd, here over Vd, we will get the current. The current will be two components. By the way, this is sine times sine. So if I expand it using trigonometric rules in mathematics, I will get two elements or two components. This is component number 1, and this is component number 2. If I look to the component number 1, I will call it ID. Okay, I will call it ID. This is the current enter after the filter to the inverter. It is voltage time current over all these are constants. Cosine phi is constant, so this is DC at the end. Since they are constants, DC. It's fine. What else? This part. This part I will call it ID2. What it contain? It contain, forget about cosine. I will name this part, arrange it and name it in this way. It will be constant time cosine 2 omega t minus phi. Forget about phi, which is, let me say, the phase shift, but omega t, 2 omega t, what this mean? This mean that the current at the input contain two components. One of them is DC, which will enter to the inverter. And the second one is AC, but it have double or twice of the angular frequency of the fundamental. Okay, so two components composite on with each other. If we deal with them, we need to talk about superposition theorem. But at the end, there is DC and there is AC component in this current. Now, if I sketch this one, we know the voltage. Voltage, as I sketched many times. This is the fundamental, as you can see here, fundamental. And this is how it look like when it come, before we let me say, filter it. Now, if I come to the current, we know that ID, the constant here, is a constant DC. Okay, this line. Okay, let's continue. And if I come to the fundamental, to the ID, sorry, which enter to the inverter, I will find that it contain IO. First of all, IO is this dotted line, dotted sinusoidal, and ID2, which is the component with double frequency, two frequency, as you can see here, this one, double frequency, two peaks, okay, for one cycle, okay, or two waveforms for one cycle. And ID, which as you can see here, this one, increase, decrease. So it's disturbed, it's distorted. Now, why this happen? Why this happen? It's happened because two reasons. The first reason is, as you know, when we produce DC from rectifier, even if we have high capacitor at the output, we still have fluctuation, we still have some sort of ripples. So it's not smooth DC, always we have ripples. Okay, if it is, let me say, solar cell, the same thing. And the second one, this distortion happened because of the AC part produced in the circuit. And this AC part is having double frequency, which will distort the current enter to the inverter. The inverter need to handle this also. We increase the elements of the, or let me say, we modify or modulate or tune, let me say, tune is the right word. Tune the filter, we can reduce this harmonic much. And it will be good for the inverter, for the load, and for the supply. Now, if we repeat the same discussion now, but for unipolar, you remember we mentioned that there is bipolar pulse width modulation, there is unipolar pulse width modulation, okay? For bipolar, we trigger or we control the switches as a pair, okay? Every two together, one from leg A, one from leg B. But in unipolar, no, we control A separately from B. There's no connection, which means that I need to have two control signals, one for leg A, one for leg B. As you can see here, you see here, This one is control signal for one leg, let me say leg A, and this negative one for leg B. Okay, carrier signal is the same, which is sawtooth, or let me say triangle. Now, when I sketch the voltage on leg A, okay, it's look like this waveform. This waveform tell me that in the positive part of the waveform, we have long period for on. In the negative part, we have short period for on, for the switch on time. Opposite will happen for leg B. Now, if I subtract, we say that the output equal VAN minus VBN. If I subtract them, I got this waveform. Now, have a look at this waveform. What it tell me? It tell me that, first of all, the fluctuation here between 0 and VD for half part of the time, and between 0 and minus VD for the second part of the time. If I compare it with bipolar, you remember bipolar, it go down. The fluctuation is high, okay, in this way, and the same thing for the other one. So this, from the signal, you can't distinguish this is bipolar or unipolar. Now here, the modulated frequency reduced, but the sideband is still there, as you can see here. You see here? It's reduced almost 0, but the sideband harmonics still there. How it look like the DC side, let me say current. Let me say there is some sort of similarity between this one and the previous one for bipolar, okay? But the only difference here, we have two components. You see here, I sketch here one component. You see, this is one component. It's a fluctuate. You see, it is not going down, similar to bipolar. In the previous, this one, you see here, it's going down. While here, it's not going down. It's only positive for one leg, negative for the other leg. By the way, you may say, what is this one? Why I didn't sketch, I mean, the book here, the textbook, or let me say the material taken from this textbook, did not sketch it here, because if they sketch it, you may confuse and think that it's going down. No, it's not going down. This is for the second leg. Here he sketched only the first leg. Also, the discussion, as I mentioned here for unipolar, that for linear or over modulation is the same. The only difference is we have VD. We don't have VD over 2. Now let's apply this on the next example. It's similar to the previous example. Earlier here, we use unipolar. And when we use unipolar, we can go for even frequency modulation. We can't go for even. Still, it's acceptable. Okay. So if I go for even, okay, I can do the same. I'm finding, you can see the value is the same. It didn't change from the previous example because it will not affect the voltage. Voltage is the same. VD over square root 2. The ratio here also, it will be the same. But you see, I took only two components because the main component, the odd one, has been cancelled. MF, 3MF, 5MF have been cancelled, so I don't need to take them. I take only 2MF plus minus 1 or plus minus 2 and so on. No need to have many because they are reduced already because it is unipolar. Now, you remember when we started with the inverter, we mentioned that we have pulse width modulation. We discussed it, unipolar, bipolar. We also square wave. We discussed it also. Now the third one was single phase voltage cancellation. As you can see here, it's the same single phase, but what we are going to do, not pulse width modulation. No, what we are going to do, we will switch and for leg A here and leg B here, but we will control the time for how long it will be switched. I mean, normally we switch leg A as example, 180 from the time for A positive and another 180 for A negative. Now in this situation, voltage cancellation, we will not switch it for 180. You see, What we will do, we will change it. We'll play it with it as example here. I mean, this is leg A, or let me even let me assume that I switch it here at 180. This is 180, and this is for 0 for another the remaining time, 180. When I come to B, I will not switch it here at 180. I switch it before the time before this. What this mean? This mean when I come to sketch it, let me change the color. Okay. When I come to sketch, we say that V out equal VA minus VB. Let me take them one by one. From here to here, VA is VD, and VB is 0, VD minus 0, VD. I have here. From here, we have VD minus VD, it will give 0. Now here, 0 minus VD, it gives minus VD. Here, into this point, into 0 minus 0, 0. Here, VD minus 0, VD. Oh, there is change. If I increase, if I call this angle to be alpha, if I increase alpha or decrease it, we will see that the output will be changed. Okay, I can't derive formula for this. I know how to derive formula for square wave. It's similar, but here from minus pi over 2 to pi over 2, V cosine, if I take it in this way, okay, from minus pi over 2 to pi over 2, or sine, just integrated as a sine, it doesn't matter. If I assume that beta, taken here the time for on to be 180 minus alpha. If I assume beta is this value, 180 minus alpha over 2, in this way split it, then I will integrate it from minus beta to beta. I did the integration for this part, then I got this formula. What this formula tell me? Let me read the formula. This is square wave, we know it, by VD. This is a square wave. But it is multiplied by sine beta. Increase or decrease beta will increase or decrease this voltage, respectively. Right? When we change beta, we change the sign, the voltage will change. So it means we control it. Now we control it by controlling beta. Beta reflection of what? Of alpha. Alpha reflection of what? The let me say collapse, or let me say the overlapping between the two signals for leg A and leg B. This overlapping will cancel part of the voltage. Can we apply it for three phase? No, we cannot. This is only for single phase, for this situation particularly. One more issue on the load. On the load, after I discuss the input here, the filter, the inverter itself, okay? Now let's go to the load. If I assume my load is induction motor, we have here inductance, we have back EMF, okay? Now, the inductance here, we'll see two components, the voltage across the inductance. VL1 plus the ripple, fundamental plus the ripple. Fundamental is coming from the forced voltage, but ripple, okay, because of the fluctuation of the circuit. So if I use superposition theorem and split them, I split here for ripple and split here for forced. For ripple, V ripple, the one, will only feed the inductance. So voltage equal 1 over, I mean, you remember VL equal L di over dt. If I want to calculate the current, I will say di equal 1 over L V integration dt, right? And for the forced, we have the voltage coming here from the inverter times inductance times back EMF. This is the block diagram as we learn in level 2. But let me focus on the current, ripple current. Ripple current, as I mentioned, 1 over L, integration the voltage ripple. Okay? When we integrate it to calculate the area under the curve, we got how much ripple in my circuit. This is one of the elements or the specification of the circuit. You want to design inverter, yes, but you need to control the harmonics, control and current and voltage, control the ripple. Ripple is important because at the end, this will disturb the operation of the load. This will affect the functioning of the load. Now, how it look like this ripple? If I come, don't forget, we are integrating the voltage, okay? Which voltage? Ripple voltage. Now, how I calculate it, let me take square wave. Square wave, this is the one we come up with, the voltage, which is square wave. And the fundamental supposed to be dotted one. If I subtract fundamental VO1 minus VO, it gives me the ripple voltage. This is V ripple, right? Then when I subtract it, it looks like this. It's clear, see, I mean, this part will be loose, so the remaining is the other part, okay? Now, if I take this voltage and integrate it here using this formula, I got this ripple current. This ripple current, its peak to peak is high. Less fluctuation, but its peak to peak is high. It's peaked at 180. Now, if I repeat the same discussion, but for pulse width modulation circuit, this is square circuit, pulse width modulation circuit here. And this is my output. Now, before I go further, this output, is it for bipolar or unipolar, and why? This is a question to you. Anybody can answer this question? The output here is bipolar or unipolar, and why? Ladies, gentlemen. Should I answer? Okay. I mentioned for it many times. Okay, just please this time don't forget it. You can see here. The voltage fluctuate between VD to minus VD. So this is what? Bipolar, right? Bipolar. So if it is unipolar, it will fluctuate between 0 to VD and 0 to minus VD in this way. And then in this way. We explain it just a few slides back. Now, if I subtract fundamental from the output voltage, it gives me this waveform. Now, when I integrated using the same previous formula in the previous slide, I got this waveform for the ripple, current ripple. Okay. Now, this tells me that you see the fluctuation, I mean, the peak to peak value is smaller than this one, but the fluctuation is high, more fluctuation, as you can see here. Now, for harmonics, the same discussion for one leg applied here. You remember we defined the harmonic factor. Harmonic factor, it's defined to be how much the contribution of each harmonics compared to the fundamental. Total harmonic distortion, we define it many times. Okay, just to remind you, it's considered to see the content of harmonics in the signal and how far it is from the sinusoidal, or let me say from the fundamental signal. And distortion factor, you remember when I talk about distortion occurs and we have part of the distortion is signal, AC signal with double the frequency, okay, which is called second filter here, so using second order filter. So how much the distortion without using second order filter, okay? Give me the distortion factor, how much the distortion. Lowest order harmonics is the closest harmonics to the fundamental. It means if I have 1, 3, 5, 7, this is the fundamental is 1, fundamental here, sorry, is 1. This is the lowest order harmonic. If I have 1, 5, let me say 7, the lowest order will be 5. If I have 1, 7, 9, and so the lowest order will be 7. So which one is the closest? If other cancelled, which one is the closest to the fundamental? And also the same discussion for using a freewheeling diode. We discussed this circuit, but for one leg, okay? Now here, freewheeling diode will provide another path. As you can see here, this increase will handled by two switches, one from leg A, one from leg B, and here it will be handled by 2 diodes, and then again by 2 switches, 2 diodes, and so on. The same formula derived before, I don't need to go through them. It's the same formula, just one difference here. It's VD or VS. It's not VD over 2 or VS over 2. As you can see here, VS, not over 2. It means we multiply by 2. The same thing for current, the same thing, which is output current, the same thing for the DC current. We derive this formula, we derive this formula, and we discuss them. I will stop here. Tomorrow I will give tutorial on this, some problems solved after we got the information about the fundamentals of single phase. Tomorrow we'll solve some problem related to this. Do you have a question?